Thank you, and thanks to everybody who showed up. It sounds like some fun was had last night, and I'm glad everybody made, or most people made it to the first lecture. So today I'm going to continue on and talk a little bit more about leptogenesis, and then change gears and talk about a very different mechanism for baryogenesis called electroweak baryogenesis. So for leptogenesis, we were looking at the minimal so-called type 1 seesaw, where we add new heavy left-handed, we add new heavy left-handed gauge singlet, so-called right-handed neutrinos. With some coupling lambda. And these heavy neutrinos also had a so-called Majorana mass term. And the structure of this mass term implies that these heavy right-handed neutrinos are Majorana particles. They're their own antiparticles. And from this, in a basis where these masses are real and diagonal, and these things are potentially complex, it's possible to get a decay symmetry. And if you recall, our decay symmetry was the difference between N1 going to, Ni goes to LA H minus gamma Ni goes to L bar A H dagger divided by the sum of them. So the sum of them is the total decay rate of the Ni state, and in the numerator I have the difference. So I have the difference between the relative decay rate, or if you like, the relative decay probability to go into lepton plus Higgs versus anti-lepton plus anti-Higgs. So I have an explicit expression for this decay symmetry, but for this difference to be non-zero, you need CP violation. So in this case, the CP violation comes in the phases of this new Yukawa matrix. And going to one loop, you get an interference between the CP violation in the phases from these couplings, with real phases coming from intermediate shells going on shell in loops. But the upshot of this is, with such a decay symmetry, let me specialize to the case where I only care about the lightest of the heavy neutrinos. I only care about the N1 state, where my labeling N1, N2, N3 is in order of increasing mass. So the N1 is the lightest of the heavy neutrinos. So suppose I come along and I've got a big box. I've got a big box full of N1s. And my big box of N1s, they don't hang around forever. They decay eventually. So I start off my big box of N1, and I wait for a little while. And eventually, the N1s decay. And the N1s decay either this way or this way into either leptons or anti-leptons. But because I have a decay symmetry, for example, for a positive decay symmetry, I'm going to get, on average, a few more leptons and anti-leptons in my box after all these decays happen. So most of the decays will be fairly symmetric, but I'll get slightly more leptons and anti-leptons. So now I've got a box with some leptons, some anti-leptons, but a few more leptons and anti-leptons. And I wait a little bit longer, and then the Svalerons come along. The Svaleron transitions come along. And the Svaleron transitions take the net lepton number I produced in these asymmetries, and they turn it into some linear combination of B and L. Where, okay, this is bad notation, but this is just some linear combination with coefficients A and B. This little b has nothing to do with that b, sorry. Okay, so this is roughly, this is the idea of how leptogenesis works. You have decays of a heavy right-handed neutrino. CP violation gives you this decay asymmetry. This produces a few extra leptons compared to anti-leptons. And this lepton asymmetry is then reprocessed by the Svalerron transitions into a linear combination of B plus L. And it's this leftover B that I care about at the end of the day. So I want to do two things to fill in the story a little bit more. my picture of just a box of N1s going and decaying away and not worrying about anything else is overly simplified. In principle, I need to deal with a thermal plasma of N1s. And when they decay, there's also a chance that the decay products will scatter with each other. And these scatterings can also violate lepton number. And these scatterings can actually wash out the net lepton number I produced in the decays. I can also have things like inverse decays. So in a thermal plasma, you can have 2-to-1 processes where the final the final one state is sort of eaten up by the plasma. So I want to worry about these thermal processes that are going to tend to wash out the lepton asymmetry I produce. But before I get to that, I also want to talk about this Sphaleron reprocessing. So the Sphaleron reprocessing is important for leptogenesis. It's also really important for just about any other baryogenesis mechanism that takes place above the weak scale. So let me remind you of a formula we had earlier. If I have some particle psi and its antiparticle psi bar, I assume these are distinct. In general, I introduce a chemical potential for them. And I'm going to assume implicitly that psi bar annihilation is very fast. So the chemical potential of the antiparticle is minus the chemical potential of the particle. So in this case, the number density asymmetry in the limit of a small chemical potential compared to the temperature is going to be either g psi mu psi t squared over, let me get the 2's right, 6, or g psi mu psi t squared over 3, depending on whether it's a fermion or a boson. So the 3 versus the 6 comes down to Fermi-Dirac versus Bose-Einstein statistics. But okay, we'll mostly be dealing with fermions here, but in any case, it's essentially the same expression up to a factor of 2. Now, this is only the leading.
What is U?
This is the chemical potential.
Oh.
So remember, mu psi is the chemical potential. And mu psi, recall, is minus mu psi bar. Okay, so this is only a leading expression in an expansion in chemical potential over temperature, but typically we will have temperatures that are way bigger than chemical potentials. So this linear approximation is a very good one. So we're going to do this for essentially all the stuff in the standard model, and we're going to make a number of assumptions. So these leptogenesis processes tend to happen at very high temperatures. But not temperatures that are too high. And it turns out that sort of these highish but not too high temperatures, so high compared to the weak scale, but low compared to the Planck scale, at these high but not too high temperatures, essentially all the standard model interactions are in equilibrium. So all the standard model scatterings and this and that are in equilibrium, up to maybe a few exceptions, but I'm not going to worry about the exceptions here. So what we want to do is figure out how sphalerons reprocess an injection of lepton number into some final linear combination of baryon and lepton number. So for that, we're going to write down all of the chemical potentials for standard model particles. And we're going to essentially solve the coupled system of equations and ultimately express them and use those to do the reprocessing, assuming all these processes are in equilibrium. So as a starting point, let me remind you what the sphalerons do. A sphaleron corresponds to something that looks like a QQQL operator cubed. So you shouldn't actually think of this as some effective operator in your action, but the transition induced by the sphalerons is equivalent to the transition amplitude you would get by taking this operator and putting it between initial and final states. So this operator describes the particle content of a Sphaleron transition. And specifically, the cubed here really means that I have one of these for the first generation, one of these for the second generation, and one of these for the third generation. So the relation implied by sphalerons, assuming sphalerons are in thermodynamic equilibrium, is that if these processes happen, I have that I get 0 is equal to the sum of 3 mu qi plus mu li, where mu qi is the chemical potential for the ith generation of the left-handed quark doublet, and mu li is the chemical potential for the ith generation of the left-handed lepton doublet. So if you recall, chemical equilibrium, if I have a process A plus B goes to C plus D, just to remind you of this, if I have a process A plus B goes to C plus D, and the rate for this process is fast compared to the Hubble, this implies that the chemical potentials that I would write down for the individual states satisfy this constraint. The sum of the initial and final state chemical potentials are equal, and then I can move these around for cross processes and so on and so forth. So if I apply this to the Sphaleron, this is the final relation I get. So this is the chemical equilibrium condition implied by sphalerons. So I'm going to take this expression, and I'm going to combine it with other standard model reactions that also give you other relations between the Q's and the L's. Now, if my standard model is more or less in equilibrium with itself, including the standard reactions, my chemical potential for hypercharge will be the same as the chemical potential for SU2, which will be the chemical potential for SU3, the gluon, and these are all 0 because I can have processes where I just spit off a vector boson for free. I have other processes like I've got other stuff like standard model Yukawa interactions. So this is a Sphaleron. If my standard model Yukawa interactions are in equilibrium, these relate a Higgs on one leg with a right-handed quark and a left-handed quark, or right-handed lepton and left-handed lepton, and these are going to imply relations of the form chemical potential for the Higgs doublet. Let me try to make sure this, plus the chemical potential for Qi is equal to 0. And I get this for every generation, plus in between generations, because of off-diagonal Yukawa mixin. So I take this, and I do this for all the standard model reactions I can think of, assuming they're in equilibrium. And I combine them with two more conditions. So the two more conditions are, these are the SU2 sphalerons. It turns out that there's also a related SU3 sphaleron compared to, effectively jumps between different SU3 vacua. And that gives me an additional relation between chemical potentials of zero is sum over all the generations, 2 uqi plus mu ui plus mu di. And sorry, there's a minus sign here. Okay, so I take all these relations between chemical potentials. I add one more constraint, which is hypercharge neutrality. So I don't want a net charge plasma. Ultimately, this is related to electromagnetic charge neutrality. You don't necessarily want to. You don't necessarily want an electrically charged universe, and this gives me one additional constraint between the chemical potentials, which is that for hypercharge, for net hypercharge neutrality. And let me see if I can get this right. So I won't write out everything, but the condition for hypercharge neutrality is this is the chemical potential for the Qi. So this gives me an excess of left-handed quarks over effectively the left-handed doublet antiquarks. And the hypercharge is 1/6, and the number of them is 6. So I've got 6 I have 2 elements in the doublet and 3 colors each. And I'm looking at a two-component Weyl fermion, and this gets me the 3 degrees of freedom. I've got 3 for the up quark, because I have 3 colors, but no doublet, and I've hypercharged 2/3. And I keep on going, and I do this for all the other elements, and I get this additional relation from hypercharged neutrality. So I take all these constraints, and there are a lot of constraints, but you take all these constraints, plug them in, turn the crank, and finally, we're going to define baryon and lepton number chemical potentials in the following way. So this is the net number density of baryons. This is the net number density of leptons. And these relations are used to define these so-called baryon and lepton number chemical potentials. So in terms of these baryon and lepton number chemical potentials, solving for the whole system, actually, sorry, before I solve for the system, let me solve for the chemical potentials. It turns out that this definition, if I add up all the contributions to the baryon number density, this implies that the baryon chemical potential is going to be sum on I to mu qi plus mu I plus mu di. So I effectively have 2 kinds of quarks from the left-handed doublet, one from the right-handed up, one for the right-handed down, and then I sum this over generations, and for each color I get 1/3, but that's cancelled off by the 3 colors I have for each quark type. So this is my chemical potential for mu b. For mu l, I get a similar sum on I, and here I get 2 mu li plus mu ei. Okay, so in terms of these definitions of chemical potentials for baryon and lepton number, and all my other constraints, you take this big system of linear equations, you simplify and solve, and what comes out at the end of the day is you get the relation for mu b and mu l. So mu b turns out to be a constant I'm going to call Cs times where the CS coefficient, so the CS doesn't stand for Chern-Simons, the CS, I don't know why it's called CS, it's a historical thing. Just a second, is, let me write down the number and I'll answer your question. Okay, a question? Well, okay, so first of all, so this is the number density. So I just add up numbers of particles. And I use this to define this chemical potential and that chemical potential. So now, if I go back and I think about my expressions for the things that contribute to the baryon number, the things that contribute to the baryon number are going to be left-handed quark doublets, right-handed up quark, right-handed down quark. And then I normalize that by the number of degrees of freedom. And I use the fact that the number densities of the left-handed and right-handed quarks are related to their chemical potentials this way. Put everything together, and this is what comes out. So this expression should be seen as a definition of mu b and mu l. And if I relate the number densities and then convert it to chemical potentials, I get these relations. Yeah, incidentally, the reason why chemical potentials are useful in place of number densities is the number density of a particle is going to depend on how many types or how many copies of it. So for example, if I have 3 colors of a quark, my total number density of quarks will have a factor of 3 on it. But if I have a single reaction involving, let's say 1 or 2 quarks, I only involve one color at a time, or one of those quark colors at a time in each particular type of reaction. So in that sense, if I kept around this extra color factor, I wouldn't get the right chemical potential relation. Okay, but anyway, back to this result. I've got my mu b and mu l, and the final result at the end of the day, after turning all these cranks and simplifying, is that you can express the final baryon density, which is linearly dependent on mu b, and the final lepton density, which is linearly dependent on L, in terms of the B minus L, the effective B minus L chemical potential. So this is useful and important. It implies two things. So first of all, suppose I started off, and instead of injecting a lepton number, suppose I had a different theory where for some reason I just magically injected a B plus L charge. So if I inject a B plus L charge, instead of talking about B and L individually, I can change my basis and talk about B plus L and B minus L. So in this basis, if I inject a B plus L, my B minus L is 0 in this different basis for mu B and mu L. In that case, what this expression says is my B minus L gets washed out by the sphalerons. So if the only thing I inject into my plasma is a B plus L, the sphalerons come along and eat up that B plus L and get rid of it. Now, on the other hand, if I inject a net B minus L, corresponding to a non-zero mu B minus mu L, I do get, at the end of the day, a final mu B and a final mu L. They're not minus of each other because I have extra constraints. But I can compute them in terms of the CS coefficient that's roughly 1/3. So going back to my leptogenesis story, what happens, at least in this kind of instantaneous injection picture, is I inject a net L, and injecting a net L is equivalent to injecting a net B minus L charge. With B minus L charge is just equal to, in this case, the L charge that I inject, or minus the L charge that I inject. Then the sphalerons come along, reprocess this, and give me, at the end of the day, a final B charge and a final L charge that's different from what I started with. Any question?
Sorry, basic question.
I'm pretty sure it's 79. I think that's oh, sorry, it's sorry, 22 and 13. Sorry. Okay, I just mistranscribed it. So the 28 over 79 is right. It's about 1/3. Maybe you're thinking of supersymmetry, which you have extra stuff floating around that changes the numbers. But okay, in any case, it's about 1/3. It's not 0. It's not 1. Yes?
I don't know if I missed anything with the squiggles and mu L and the number densities.
Oh, I was just emphasizing the point that these are definitions. Okay, it's not some magic notation. Okay, so this is the story of sphalerone reprocessing. It plays an essential role in leptogenesis. So if I only had leptogenesis, if I only had leptogenesis without sphalerons, I wouldn't get baryons. So this specifically is how baryon number violation comes in for the mechanism of leptogenesis. Leptogenesis on its own, given that I wrote down these interactions, has built-in lepton number violation. But I also need the baryon number violation to get the final baryon number, and I see that coming out specifically from the sphalerons. Now, I should also mention that there's a class of theories of baryogenesis that operate a lot like leptogenesis, but that are based on grand unified theories. So grand unified theory is a theory where you take your SU3 cross SU2 cross U1 gauge structure, and you embed it in typically a simpler group, if not a simple group, like for example SU5 or SO10. And for example, in SU5, you also combine the standard model matter fields into irreducible representations of this unified group. So in the case of SU5, it turns out that you mix quark and lepton fields within the same SU5 representations. And this means that there exist gauge interactions and possibly Yukawa interactions in the grand unified theory that violate B and L. Now, it turns out that, at least for a lot of the minimal grand unified theories people write down, B minus L is a good symmetry, but B plus L is a bad symmetry, in the sense that the grand unified theory explicitly breaks B plus L, but it preserves B minus L. And in mechanisms of gut baryogenesis, people had initially thought, okay, I'm breaking B plus L, my heavy gut stuff is going to decay with an asymmetry, so similar to how this stuff works. But this seemed very promising. But there are a few problems. But one of the problems specifically is that if you're only violating B plus L, your sphalerons come along and get rid of it. So if you only inject B plus L in the plasma, the sphalerons wash that out. So even if you had this very cool, very interesting gut theory, if it only violates B plus L and generates a B plus L charge, your sphalerons actually ruin what you wanted to produce. So this is a word of warning about sphalerons. They're sort of a double-edged sword. On the one hand, they can help you if you inject a net B minus L. But if you don't inject a B minus L, if you violate baryon number in such a way that you only inject a B plus L, they tend to wash you out. So sphalerons are not necessarily a helpful thing for baryogenesis, but one way or another, they play an important role. OK, so coming back to leptogenesis, this is the story of the sphalerons reprocessing. I initially inject an L from the heavy neutrino decays, and then this gets reprocessed into a net, into a combination of B and L charges. The last thing I want to talk about is how the injection actually occurs. So there's an idealized picture where I just take a nice, perfect box full of N1s. I'm walking around town. I've got my box of N1s. They go poof. They decay. I get some extra leptons versus anti-leptons. They're reprocessed by sphalerons, and I get baryons at the end of the day. This is great. But cosmologically, the story is more complicated. So cosmologically, I don't just have a box of N1s. I've got a big, complicated thermal plasma. And I have to worry about additional processes within the theory that can counteract the decay symmetry. OK, so actually, is that one mine? I think that one's mine. That one's OK. Sorry. OK. So the way we describe the cosmological evolution of the densities is through a set of Boltzmann equations. So I wrote down one Boltzmann equation for you, I guess it was Tuesday, describing dark matter freeze-out. And Boltzmann equations describe the approach to chemical equilibrium, or I should say the approach to equilibrium. So the Boltzmann equation is relevant here. I'm going to use a slightly different set of variables than I used previously. So I'm going to define what are called yields as the ratio of the number density of a particle type I relative to the entropy density. So little s is an entropy density. And the reason this is useful is that if I don't have any interactions, if my universe is just expanding and I don't have any reactions, with no reactions, my number density would just dilute as a to the minus 3 from the expansion. And because the expansion of the universe is adiabatic, as long as everything's well behaved, my entropy density also goes like a to the minus 3. So the motivation for using yields instead of just individual number densities is that as long as in the absence of departures from equilibrium and interactions that change the number density ni, this yield is just a constant. So using yields is handy because after something freezes out, like dark matter, for example, the yield you get is just a constant. So I'm going to use this yield variable instead of ni. This is just changing a variable. And I'm also going to use a z variable, which I'm going to define as the mass of the N1 state divided by the temperature. So I'm going to use this variable instead of time. But as I go forward in time, this z variable, the z variable, is going to increase because my temperature is going down. So in terms of these variables, the Boltzmann equations that describe this leptogenesis system, and specifically I'm going to look at the system where I have N1s predominantly. So I'm going to assume that my heavier right-handed neutrinos are much heavier and don't contribute appreciably to the decay symmetry. I have one Boltzmann equation for the density of the N1 state that I'm going to write as a differential equation for y1. So y1 is the yield of of the N1 density. And the second Boltzmann equation I'm going to write is for the B minus L charge. So if you work through, I'm not going to derive this, but hopefully the result should be kind of fairly intuitive. I'll tell you what these D and S things are in a second. So my differential equation for y1 has this form. So this is the actual y1 yield that may be different from the equilibrium value. And this is the y1 value I would have in full chemical and in kinetic equilibrium. So what this equation says is, OK, up to this coefficient that I'll get to in a second, if I have, what this equation says is that if I differ from the equilibrium value, and this coefficient isn't too small, I tend to asymptote to the equilibrium value. On the other hand, if I try to put a bunch more N1 states in than equilibrium, this reaction is going to tend to push the N1 density down. It's going to push Y1 down, and it's going to tend to push Y1 towards Y1 equilibrium. On the other hand, if I start with an underdensity of Y1, this term will be bigger than this. And the minus sign will hit this minus sign, and these reactions will actually push up the N1 density to the equilibrium value. So this is my Y1 equation. My second equation is going to be an equation for Y of B minus L, where YB minus L is the yield for B minus L. And so I'll come back to these coefficients in a second, but what this term is giving me is the rate at which I generate a B minus L charge is going to correspond to the rate at which Y1 decays. So, okay, spoiler alert, D is going to correspond to a decay rate. If I have more Y1s than Y1 equilibrium, I tend to have decays that produce a B minus L charge proportional to the decay symmetry epsilon 1, which is the decay symmetry of the N1 state. Now, I also have the second so-called washout term. The W stands for washout. And this is going to describe processes that tend to cancel off the B minus L charge that I produce in the decays. So let me keep on going and move next to these coefficients. OK, so the D coefficient, and it's going to be a function of Z, is a so-called decay piece. And it's given by, OK, so up to some extra factors that come about from using these slightly funny variables. Yep. Yes. Yeah. So OK. So well, so two things. I'm not going to get into it in quite in that much detail. So I'm just trying to give a high-level overview. But the 2-to-2 stuff is actually secretly in here. OK. But OK. So let me get back to the decay coefficient. The decay coefficient is just the decay rate of the N1 state normalized to Hubble when the temperature is equal to M1. And if you recall, Hubble goes like T squared over M Planck. Now, the appearance of Z here just comes about because of the way I change my variables in the differential equation. So don't worry about this Z. And this 1 over gamma is a time dilation factor. and it's thermally averaged. And what it's saying is that if my n1s are very relativistic, they're going to have effectively a longer lifetime because of time dilation. Okay, but in any case, this D coefficient describes decays of the y1 state. So if I think of D as a decay rate, or at least roughly it's a decay rate normalized to Hubble up to this extra z variable stuff. This is saying that as long as this coefficient is bigger than about 1, I should reach equilibrium pretty efficiently. On the other hand, if this coefficient is much less than 1, I'm not going to reach equilibrium very well at all. This decay coefficient also comes in this term. And this term is describing the time evolution of the B minus L charge. So what this is saying is the decays normalized by the decay symmetry generate B minus L, a net B minus L charge with an extra minus sign because I'm making lepton number, which is minus in the B minus L. So in any case, this is my decay thing. This S piece, I'm mostly going to ignore it from here on in, but the S corresponds to scattering. And it's primarily delta L equals 1 scattering. So technically, you need to put it in for self-consistency, but numerically, it's kind of small. So I'm just going to ignore this from here on in. And the last piece, though, I want to talk about is the washout piece. And the washout piece comes from both decays and scattering. So what washout means is, suppose I've gone to all this trouble to get my decay symmetry to make some B minus L. That means that typically I have more leptons and anti-leptons in my plasma by a little bit. But if I have more leptons and anti-leptons in my plasma, that means that let's get to a second. Okay, so if I have more L than L bar in my plasma, this means that the process LH So the way to think about washout, and this is only one example of a washout contribution. So suppose I've made more leptons and anti-leptons in my plasma. If I have more leptons and anti-leptons in the plasma, it's now more likely for a lepton to find a Higgs to make an N1 than it is for an anti-lepton to meet an anti-Higgs to make an N1. Just because I have more initial states that can scatter. And this means that if this so-called inverse decay happens quickly, it's going to tend to wash out the baryon, the B minus L charge I've created. And I simply wash it out because if you have more of one than the other, it's going to be more likely to go through that reaction than the other one, and this tends to wash out the rate. Now, there are also contributions from scattering that also violate, typically with intermediate off-shell end state, that also wash out the B minus L charge. And again, it's the same story. So to get an asymmetry at the end of the day, I have to be a little bit careful. So without the washout term, my life would be really easy. Without the washout term, I would just decay my N1, and the asymmetry would turn into the asymmetry would turn into a net B minus L charge as long as I decay with a slight difference from the equilibrium density. On the other hand, with the washout, even if I make a big asymmetry, this is going to reduce it at the end of the day. So this is where departure from equilibrium comes in to make leptogenesis work. So there are different limits of leptogenesis depending on how close to equilibrium or how far out of equilibrium you are or are not. If I'm really, really far out of equilibrium, so suppose suppose I somehow magically create a bunch of n1s such that such that they decay really late with this gamma 1 over h very small. This means that the washout term will be small. My y1 equilibrium will essentially be 0, but I have a much bigger y1 than the equilibrium value. And this just corresponds to my box picture, where the n1s just decay, they make an asymmetry, and that asymmetry hangs around. This is a far from equilibrium scenario. On the other hand, if I'm very close to equilibrium, if my decay rate corresponding to my decay rate at Hubble when the temperature equal to m1 is much bigger than 1, I'm actually going to track equilibrium really, really closely. And this is going to give me an extra suppression of the final B minus L density I get at the end of the day. So we often characterize the degree that you are or are not in equilibrium by this K, so-called K coefficient, which is just gamma 1 over Hubble at t equals to m1. So this ratio of rates. So there are approximate analytic solutions to these Boltzmann equations. So okay, ultimately you just put them on a computer and solve them numerically. But they're nice approximate analytic solutions to these Boltzmann equations in these two limits. And roughly what you get at the end of the day is your final y b minus L after all these processes at the end of the day, at late times after all this decay and reprocessing and junk has happened, you typically, this is going to be epsilon 1 times a okay. So I'll put a k tilde. Let's say. So people often write the final result of leptogenesis as something that goes like the asymmetry. Oh, there should be a minus sign here. Times an efficiency factor. So the efficiency factor just takes into account essentially how far off from equilibrium you are when the n1 decays happen. And okay, I have some more stuff in my written notes about this, but the whole story of leptogenesis and the Saharov conditions are kind of encapsulated in this final result, in the sense that this epsilon 1 tells you that you need C and CP violation to make these leptons. You also need lepton violation to get a non-zero value. You need baryon number violation to get a non-zero B minus L through the sphalerons. And finally, this efficiency factor, for the efficiency factor to be non-zero, you need a departure from thermodynamic equilibrium. So this final result essentially encapsulates all the Saharov conditions as they apply to this standard type 1 leptogenesis scenario. Now, I should also mention that I've only treated this in a very simplistic way. There are all kinds of individual effects that can modify the final answer. You can have resonance effects, you can have flavor effects, you can have thermal effects, and I'm not going to touch those. I just want to conclude talking about leptogenesis with one comment, which is that there's an interesting relation. There's an interesting relation between the light neutrino masses within this scenario and the amount of leptogenesis you get. So roughly in a simplified leptogenesis scenario, our final B minus L charge, our final essentially effectively baryon asymmetry, is proportional to epsilon 1. And there's a result by Davidson and Ibarra that gives, I'm trying to get the formula right. That gives you this relation. So the maximal possible decay symmetry is less than, this is the mass of the heavy N1. This is the Higgs electroweak valve, so roughly 174 GeV squared. And this is the mass of the heaviest standard model like light neutrino. And this is the mass of the lightest standard model like light neutrino. So we know that the sum of the standard model neutrinos is less than about 0.2 eV from cosmology. And that puts that puts an upper limit on this combination. In fact, you could also put a limit on this from the largest neutrino mass difference people have found from oscillations, which is the so-called atmospheric. Oh, actually, sorry. Which is the so-called 2-3 mass splitting. But in any case, we can take what we know about light neutrinos and use it to constrain this epsilon 1 parameter. And we also have for our efficiency factor that our efficiency factor, unless you start to get weird, the efficiency factor is typically less than about 1. And what this says is for leptogenesis to work, taking into account what we know about light neutrinos and this so-called Davidson-Ibarra bound, this effectively pushes up the mass of M1 you need to make leptogenesis work. And roughly, M1 has to be greater than sort of order 10 to the 8 GeV for this particular variety of leptogenesis to create the final baryon asymmetry. So this number is actually kind of interesting. It's small enough that a lot of standard inflation scenarios will reheat above this temperature. But it's also getting high enough that, for example, if you take this scenario and you embed it within supersymmetry, you might start to worry about making too many gravitinos from reheating to this temperature. So this is just a passing remark. Let me just finish up with leptogenesis there and move on to electroweak baryogenesis. So this is sort of changing gears a bit. So leptogenesis is a very nice mechanism for creating the baryon asymmetry, in that it connects the baryon asymmetry to light neutrino parameters. And it connects the source of the baryon asymmetry to the origin of neutrino masses. On the other hand, you have to count parameters carefully to see this. It turns out, though, that if you only measure, well, if you measure everything it's possible to measure about the light standard model light neutrinos, like all their mixing angles and even their absolute masses and CP phases and this and that, it turns out that this is not enough to fully peg down what's going on in the heavy neutrino sector. In other words, just because you measure everything you possibly can about light neutrinos doesn't tell you that leptogenesis is actually the source of the baryon asymmetry. So a lot of times, okay, this is just a passing remark. A lot of times, neutrino experiments looking for a CP phase will say that, okay, we have evidence for a CP phase. This is telling us that we're starting to understand where the baryon asymmetry comes from. This isn't quite true. So I mean, it's very important they measure CP phases. This is really interesting. And seeing a CP phase within the light neutrino sector is at least, it's kind of what you expect if you have CP violation in the neutrino sector, but it doesn't necessarily tell you that leptogenesis made the baryon asymmetry. Okay, so that's just a passing rant. Let me change gears now, quite severely, to a slightly different mechanism of baryogenesis that is more testable. So leptogenesis is very nice, but it's very hard to test at low energies because recall the heavy right-handed neutrino mass that I just erased has to be larger than 10 to the 8 GeV, at least within these minimal scenarios. There are non-minimal scenarios where it's much less, but at least in this minimal scenario, it has to be very big. For electroweak baryogenesis, all the interesting action takes place in the electroweak phase transition. So it turns out, and I'll get to this in more detail in a little bit, that at very high temperatures, the full gauge invariance, the manifest gauge invariance of the standard model is effectively restored. And as you cool down through about 100 GeV or so, you have a phase transition, or something very close to a phase transition, where you go from this manifestly manifestly unbroken gauge phase to a broken gauge phase where your Higgs expectation value becomes non-zero. This is called the electroweak phase transition. And electroweak baryogenesis operates during the electroweak phase transition, provided that phase transition is first order. So a first order phase transition, in this context, corresponds to the nucleation of bubbles of broken phase within a surrounding plasma of symmetric phase. So if phi is my Higgs expectation value, you nucleate bubbles of phi not equal to 0 phase within a surrounding plasma of phi equal to 0 phase. So this is my unbroken phase, this is my broken phase, and these are bubbles of broken phase that I've nucleated through a first order phase transition, expanding out within the surrounding unbroken phase. Now, as long as the nucleation rate is big enough, I make enough of these bubbles and they expand fast enough that eventually they all come together and coalesce and combine and so on and so forth. But while they're nucleating and growing and expanding within this symmetric phase, I can have baryon production take place. So electroweak baryogenesis takes place sort of near these bubble walls. And if I zoom in on a bubble wall surface, so here's a bubble wall that has some finite thickness, and it's moving with some velocity w out in this direction. On this side, I have phi non-zero. Phi is my Higgs valve. On this side, I have phi equals to 0. And what this means, because I have a varying Higgs valve, this means that my standard model fermions on this side are effectively massless, and on this side, they're massive. And this means that when they see the wall, they effectively see a potential change. And a fermion can come in, and it can either be transmitted or reflected. And this could be, let's say, a left-handed or right-handed fermion, what have you. Now, if you have CP violating interactions within the bubble wall, it turns out you can get different reflection and transmission coefficients for left-handed versus right-handed fermions. And what electroweak baryogenesis relies on is getting an excess of left-handed fermions outside of the bubble wall, just in front of it, because of CP violating reflection and transmission coefficients. Now, if I make a net left-handed number asymmetry, remember that my electroweak sphalerons act on left-handed states. So my left-handed asymmetry is going to bias sphalerons to make more baryons and antibaryons. So I've got my left-handed stuff, and my sphalerons come along, and they turn this into a baryon charge. And I've got a baryon charge, or actually specifically, I've got a B plus L charge. And if my bubble wall just sat there, and my baryon, my B plus L charge just sat there, I'd have another sphaleron come along and eat it up and get rid of it. But what happens instead is, because my bubble walls are expanding and moving along, this B plus L charge gets sucked up inside the bubble wall. And the thing about the sphalerons is that in the unbroken phase, the sphaleron rate is fast. It goes something like t to the 4th with some numerical coefficient. On the other hand, in the broken phase, if you recall, the sphaleron rate goes like t to the 4th, but with an exponential suppression. That looks like the energy of the sphaleron configuration in the broken phase divided by the temperature. So this means that the sphalerons can be fast outside the bubble walls, but they can be really, really slow inside the bubbles. And that means that I make my chiral asymmetry, it gets converted into a B plus L by a sphaleron, and then the bubble comes along, sweeps up the B plus L charge inside the bubble, and instead of being washed out, because the sphalerons are very slow on this side, the B plus L hangs around. So this is electroweak baryogenesis in a nutshell. And again, it illustrates the three Saharov conditions. You have C and CP violation in the form of the scattering that produces a so-called chiral asymmetry, effectively more left-handed leptons than right-handed leptons here. You have B violation in the sphalerons. And finally, you have a departure from equilibrium in the sense that the wall's not just hanging around, the wall's actually zipping along pretty quickly, and it sucks up the bubbles into into a spot where they're effectively safe before they can be washed out by the sphalerons. So again, we see the three Sakharov conditions at work here. Computing this process is actually a bit of a mess. So I'll tell you about this right off the bat. Computing this process is a mess for a whole lot of reasons. You have to compute the phase transition, then you have to compute the bubble nucleation rate, then you have to compute the bubble profiles, then you have to compute the scattering, then you have to compute the diffusion of the charges and washout of the charges in front of the bubble wall, then the sphalerons, and then the sucking up probability. And OK, it gets kind of messy, but I want to give you at least a flavor of the main parts that go into the calculation. But keep this cartoon in mind as I go forward and plug away. So here I have phi non-zero, and here I have phi equals to 0. So what I mean by bubble profile is if this is, I don't know, let's say this is some z coordinate along this direction, and this is the value of phi. My phi is going to be non-zero here, and then it's going to go to 0 here. And the bubble profile is sort of the profile of it, how it goes from non-zero to 0. OK, so the first thing I need to talk about for electroweak baryogenesis is quantum field theory at finite temperature. So this is a really interesting topic. It's also a pretty messy topic. But fortunately, we'll only need a few kind of specific aspects of it. OK, so the first thing I want to remind you of is in just regular old quantum field theory, I think many of you will have seen the idea of an effective potential. So the idea of an effective potential is, suppose I have a theory with a scalar field. And OK, so a nice example is kind of like a Higgs-like scalar field where I know I've got a kind of a wine bottle potential. And I'm sure everybody sat down and minimized the Higgs potential just using the tree level, just using the tree level potential that you write down, and you find the minima, and this gives you symmetry breaking, yada yada yada. Okay, what the effective potential does is it essentially takes that tree level potential and it adds in the quantum mechanical correction to it. So by quantum mechanical corrections, I mean loop corrections, and what these do is they can change the shape of the potential a little bit. So instead of having like this, when you include quantum corrections, you might have something that's maybe a little deeper here and a little deeper there, and changes the potential a little bit. But at least in a weakly couple theory, it doesn't tend to change your potential overly radically. There's some exceptions to this, but for the most part, as long as you have a fairly robust tree level potential, the loop corrections don't change it too much. And the effective potential describes how essentially takes into account these loop quantum corrections to the potential that you go off and you minimize at the end of the day. So this is the story at just regular old quantum field theory. But we're going to be interested in quantum field theory at very high temperatures. So the regular quantum field theory that most likely you've seen has been formulated essentially with scattering in mind. And that you compute, you take Green's functions and you take stuff off to asymptotic states, and ultimately you compute S matrix elements. So in this sort of standard quantum field theory, the idea is you've got states coming in from asymptotic time of -infinity. They come in, travel through empty space. Let's say they collide with each other, and then go off to asymptotic time equals plus infinity. But except for where they meet each other, they're essentially just going through a vacuum. In the case of thermal field theory, you no longer just have a vacuum. You've got this big thermal ensemble, this big messy thing, this big goopy thing that the states are traveling through. So, for example, you can calculate the scattering of states within the thermal background. But you can also look at the properties of, for example, the equilibrium state of quantum field theory when you take into account these thermal effects. So, I want to focus on an object that we also call an effective potential, but it's technically a thermal effective potential. And we'll see that the thermal effective potential coincides roughly with a free energy density of the system. And free energies are nice because they describe the equilibrium state of the thermodynamic system, which might not be the same as the equilibrium state of the system at 0 temperature. Okay, so to take into account thermal corrections, we're just going to take our field system, our quantum mechanical field system, and just plug it into regular old statistical mechanics. So recall for statistical mechanics, for a quantum mechanical system, you have a partition function that corresponds to a trace over all quantum states of an effective density operator. And this density operator looks like e to the minus beta Hamiltonian. And I'm just going to make it a little bit fancier by putting in charges. So this beta is just a nice way of writing 1 over t. So this first piece is your usual Boltzmann factor, e to the minus e over t, but now as a quantum mechanical operator. And what I've added to this are chemical potentials. So specifically, I've added chemical potentials for all the conserved charges in my quantum field theory. So for now, okay, so I mentioned the conserved charges. For now, I'm going to ignore these and just focus on this piece, but we'll come back to that part later on. So now with my partition function, I can compute thermodynamic expectation values. And all I need to do to compute those thermodynamic expectation values is to take my partition function and stick whatever operator whose expectation value I want in the thermal ensemble, stick it in here, and then normalize by the partition function. So again, this is just regular old quantum statistical mechanics. The only difference compared to what you may have seen before is we're going to apply this to a quantum field theory system. Here's my eraser. Here's my eraser. Okay, so to apply this to a quantum field theory system, it turns out that path integrals are really handy. So let me remind you of sort of a standard path integral result. I can formulate a quantum field theory in terms of configuration states with operators acting on them. So the configuration states, let's say for a real scalar field, is just the configuration that's the eigenvalue of the quantum field operator. It's a bit like this whole like x hat x, and so okay, this is going to get confusing, but roughly at the end of the day, I'll write this way. Suppose I want to compute a configuration A at Ti going into a configuration B at time Tf. So I have some initial field configuration that has some quantum state here, and I want to find the amplitude to go to some final state. The basic result that everybody should be familiar with is that this just corresponds to e to the minus Hamiltonian Tf minus Ti phi a of 0. So my time evolution is gotten by the Hamiltonian in the usual way. And in the path integral formulation, you stick in a bunch of intermediate states. In this case, they're going to be intermediate phi and conjugate momentum states. And you stick in all these states, sum them up, take a limit to infinity. And what you get at the end of the day is this thing corresponds to a path integral. And the path integral corresponds to the sum over all phi configurations, such that I have phi a at Ti, and I have phi b at Tf. So these are my boundary conditions on the set of configurations I sum over. Sorry. Okay, so I'll just leave it this way. So this is the path integral representation of this transition matrix element. So just usual thing in quantum field theory, and this thing coincides with the action. So my transition amplitude corresponds to going from this state at Ti to this final state at Tf. These correspond to initial and final configurations of the field. And the recipe is that to get this transition matrix element, I sum over all possible configurations with these boundary conditions and then weight it by the action. So if I go and think about a partition function, if I wanted to compute the partition function, or something like that, I would go off and now I want to compute a trace. So a trace means that I compute the same initial and final state for one. But the other thing about the trace is I'm not going to, I don't want a time-dependent thing. I want to look at static field configurations. So I'm looking at equilibrium systems. But now I don't have a time evolution. Instead, if I wanted to go compute my partition function, I want to compute a trace over all states weighted by essentially e to the minus beta h. So the thing I compute for my partition function is going to be essentially a sum over all configurations of okay, so phi a of phi e to the minus beta h phi. So I have the same initial and final state, but by analogy with this form, I can think of this as a path integral after inserting a bunch of intermediate states. This thing turns into a path integral over, if you like, a bigger set of things. They're periodic. I don't want to write this. Okay, actually, I'm going to write this in a slightly different way. So it turns out that my path integral, weighted by this e to the minus beta h, in the same way that I get from this expression with e to the minus ih, delta t, to this thing with initial and final states, in exactly the same way that I do that, I can insert a bunch of states here and rewrite this as a full path integral over all possible periodic configurations that go from Euclidean time tau of equals 0 to beta. And because I want the same initial and final state, I have to sum over the boundary condition that these are periodic configurations. So in other words, phi of beta of x as my final configuration is the same as my initial configuration. And this thing corresponds to an imaginary time, in the sense that instead of having a minus I delta t here, here I just have a minus beta. So again, going by analogy, instead of having a sum over regular time, I have a sum over Euclidean time from 0 to beta, where beta is 1 over temperature. And I sum in my path integral over all periodic configurations of the scalar field. So this is how I compute the contribution to the partition function for scalars. I can also compute the contribution to the partition function from fermions. And it turns out that that fermion contribution gives me essentially the same expression, except that now, because of Fermi-Dirac statistics, I actually want anti-periodic configurations instead of periodic configurations. Okay, so anyway, this stuff is motivation. But it's motivation for the fact that to evaluate this path integral, I can evaluate this path integral using Feynman diagrams in the same way that I evaluate regular path integrals for transition amplitudes with Feynman diagrams. And the only difference here, though, is this periodicity condition. And the periodicity condition means that effectively, instead of having a four-dimensional field, I now have 3 spatial dimensions and a compactified Euclidean time dimension. So it's like I've taken my 4 dimensions, Euclideanized time, and compactified it with radius beta. And the implication for that is if I want to sum over field configurations, it's helpful to expand these in Fourier modes. And the Fourier modes appropriate for the periodic boundary condition have a Fourier expansion of the following form. Two pi cubed n of p e to the omega n tau plus p dot x. So this looks like just like a regular mode expansion that you do in quantum field theory, but now because I have compactified time, I have instead of an integral over d4p, I now have an integral over d3p with a sum over n, where the n's are periodic and they have frequencies 2 pi over beta. So I need these frequencies to get a periodic field. Oh, sorry, and I forgot an n here. 2 pi n beta. So this means that if I make tau equal to beta, I get back to where I started from. So with this expansion, you can go and compute Feynman diagrams in the usual way. And now your Feynman diagrams will involve, instead of just momentum modes, your Feynman diagrams will involve sums over these different n states. These different n states are called Matsubara modes. And you can go off and compute your Feynman diagrams in exactly the same way as before, but now instead of doing the usual integrals over time and energy, you instead replace those with sums over Matsubara modes. And at the end of the day, you can go off and compute your effective potential. You can either get it directly, it turns out it's directly related to the partition function, or you can go off and compute your so-called thermal effective potential, use the same methods you would use to compute your regular effective potential, but now using these compactified fields in the time direction. So the final result for the thermal effective potential, I could spend multiple lectures on actually deriving it, so I'm just going to give you the final result. The final result for the thermal effective potential at one loop order turns out to be just the tree level potential that I'm going to call V0 of phi, plus the zero temperature one loop potential, plus a thermal correction. So the tree level potential is just what you started with. So for example, if I started off with a double wall potential like this, my V0 would look something like a minus mu squared phi squared plus lambda over 2 phi to the fourth. But now I also include the one loop t equals 0 contribution and the delta V. So we're going to be mainly interested in the thermal corrections because these are the ones that are going to do interesting things. So the form of the thermal contribution, the delta V1 thermal, has contributions from all the bosons and all the fermions in your theory. And the contributions from the contributions from bosons and fermions are related to these so-called thermal loop functions that have the following forms. So the thermal loop functions, JB or F, as a function of x squared, are just given by let me try to get this right. Log 1 minus plus e to the minus u squared plus x squared. Okay, so at this point, things are looking a little bit hairy, but it turns out that these loop functions have very nice asymptotic forms that are hopefully somewhat more intuitive. So first of all, in the limit of low temperatures corresponding to x much, much bigger than 1, it turns out that both loop functions take the asymptotic forms of x over 2 pi to the 3 halves, e to the minus x 1 plus order 1 over x. So this contribution should look fairly familiar. So remember, my x squared, or my x specifically, is going to be the mass of I divided by the temperature. And in the limit where the mass over the temperature is much larger than 1, I get this exponential suppression. So the exponential suppression is our familiar Boltzmann suppression for very massive for states that are very massive compared to the temperature. And in fact, if you look at this expression looks a lot like the expression for for the number density of a very massive particle. So this is the large X asymptotic form, valid for. This is the large X asymptotic form, valid for effectively low temperatures. The small x approximation, corresponding to high temperatures corresponding to the masses, is a bit messier. Okay, let me just pi squared over 12 x squared minus pi over 6 x plus dot dot dot, so x cubed plus order x to the 4th. And my fermionic loop function is slightly different. This is some constant plus the leading term in x is minus pi squared over 24 x squared plus order x to the 4th. So we're going to use these asymptotic forms in just a second. One last comment, though, is the masses that go into these loop functions aren't just your regular masses. So specifically, I'm looking at the value of the effective potential for a background value of the phi field. So I've got some phi field, and I'm moving around in the potential. And specifically, when I write mi, I mean mi as a function of phi. So at this point, the result might be looking a little bit cryptic, but let me apply this to the standard model. So for the standard model, we're going to match up our phi with the Higgs background value. So for the standard model, we have the 0 potential. It's going to be minus mu squared h squared plus lambda over 2 h to the 4th. where H is my Higgs field, and this is going to be G0, sorry, G plus, and just get my notation right. Just a second. And then the lower component, I'm going to have a background value plus a 1 over root 2 H plus I G0. So the G plus and G0 are the Goldstone modes. The phi is going to be the background value of the Higgs field. So I'm going to vary it along the usual non-zero direction that we normally identify with the Higgs vev. And then here's my physical Higgs boson within that background. So I take this form of the Higgs, I plug it in here, and I look at everything as a function of phi. So this means that as a function of phi, V0 of phi is just going to be minus mu squared phi squared plus lambda over 2 phi to the fourth. And minimizing this is just the usual thing you do when you minimize the Higgs potential at phi level. So this is the minimization that you should all be familiar with. And you find that the minima of these correspond to some non-zero value of phi that corresponds to the Higgs vev. But now we're going to add in these thermal and loop corrections. So to add in the thermal and loop corrections, I need to also take into account contributions from the other particles in the theory, the non-Higgs particles in the theory. And the most important ones are going to be the ones that couple most strongly to the Higgs. So specifically, the top quark. And the top quark is going to have, in this case, is going to have 12 degrees of freedom. And the mass of the top, as a function of this background, is just going to be the top Yukawa times phi. So I'm going to take this value of the field-dependent top mass, I'm going to plug it into my loop functions, and use this as and look at the thermal correction it induces on the potential. Now I also have corrections from the W and the Z. And there's some initial ones, but I'm just going to, for now, look at the top W and Z. So the W has 6 degrees of freedom, and the Z effectively has 3 degrees of freedom. So implicitly, I'm including longitudinal polarizations in these. And MW of phi is G squared phi squared over 2. And MZ of phi is going to be G squared plus G prime squared phi squared over 2. So these will be the leading contributions to the corrections to the effective potential to the Higgs. And I'm going to focus mainly on the thermal corrections to the Higgs. And specifically, I'm going to look at the thermal corrections to the Higgs in the high temperature limit, where the temperature is very big compared to what would be the field-dependent values of the top and W and Z masses. Yes?
Are these thermal corrections already renormalized in this expression, or do you have to impose some additional conditions?
Yeah. So you need to renormalize the one loop. You need to renormalize the zero temperature correction. But thermal corrections effectively automatically cut off in the UV, and there's no additional renormalization needed for those. So, put another way, all the UV stuff, all the UV stuff you worry about can be put in the zero temperature part of the full. Yeah. So if you're smart, your counter terms don't depend on temperature. And I guess an intuitive way to think about this is renormalizing affects the UV part, and renormalizing that part shouldn't care about the light parameters which correspond to the temperatures. So the UV part way above the temperature shouldn't care about the temperature. So it turns out that as long as you don't choose a silly renormalization scheme, you can lump all the renormalization into the zero temperature piece. That's a good question. Okay, in any case, let me get back to the thermal corrections. I'm going to basically ignore the zero temperature one loop corrections because they're not going to change the story too much. So I'm going to focus on the thermal corrections. And specifically, like I said, I'm going to look at the thermal corrections in the high temperature limit. That corresponds to small x. And at small x, the leading pieces are these quadratic parts. So I go and I look at my quadratic corrections. To the Higgs potential. And keeping the leading thermal corrections at high temperatures, what I find for my thermally corrected Higgs effective potential, let me just find this, is my VF of phi and t that includes the leading thermal and one-loop corrections. Turns out to be the thing I started with, but with a correction that comes from the thermal pieces, minus sign here, phi squared plus lambda over 2 phi to the fourth, where this d is roughly, let me try to get it, 1/8 2y top squared plus 3g squared plus g prime squared. So this correction is coming from taking these field-dependent masses, plugging them into the thermal corrections for JB or JF that come in over here, and the leading correction goes like x squared. So remember, x corresponds to mi of phi over t, and the full correction involves JB or JF times t to the fourth. And you take this stuff, lump it all together, and what you find for the leading correction to the thermal effective potential is this new piece. So this is the leading thermal correction to the Higgs effective potential at very high temperatures. So high temperatures corresponding high temperatures relative to the masses of the W and the Z and the top at that particular field value. Yes? Oh, sorry. There you go. Yeah, the top is right, the W, okay. Okay. In any case, yeah, so the x squared piece gives me a phi squared piece. And this is what I get from my potential. So the thing about this potential is if I make the temperature big enough, this term becomes positive. So remember, our standard story for Higgs electroweak symmetry breaking was I've got this wine bottle potential. And the reason it goes down at the origin like this is precisely because the coefficient of the quadratic piece that dominates at small field values is negative. What happens at finite temperature? So, OK, I should also mention that there's a temperature-dependent constant piece that I'm dropping. What happens at finite temperature is if I make my temperature a little bit non-zero, this piece becomes a little bit less small, and my potential becomes a little less shallow. But if I keep on cranking up the temperature more and more, eventually I get to a state where my thermal effective potential now looks like that. And my thermal effective potential, once it looks like this, means that instead of being stabilized over here at the absolute minimum, my global minimum is now going to be here. And what this means is that instead of having a non-zero phi at the minimum of the global effective potential, I now have, at sufficiently high temperatures, a zero field value at the minimum. And this corresponds to so-called gauge symmetry restoration. So the thing I want to point out here is, and this is a neat thing about thermal corrections. The so-called electroweak symmetry, which, OK, it's not actually a symmetry, but let's not get into that. The whole SU2 cross U1 invariance, which is at least hidden at low energies, so quote unquote broken, is restored at sufficiently high temperatures. And this also means that if I start at a high temperature and cool down, eventually I'm going to go from a global minimum at zero field value to a global minimum, or to a global minimum at a non-zero field value, and that's going to correspond to what we call the electroweak phase transition. And it's in that electroweak phase transition that we're going to do electroweak baryogenesis. To make electroweak baryogenesis work, we need a first-order phase transition. And at this point, this potential doesn't predict a first-order phase transition. And it doesn't predict a first-order phase transition because if I think about starting here and just lowering the temperature, I just smoothly and adiabatically evolve into a non-zero minimum. And that's not what I need for a first-order transition. A first-order transition is going to require a barrier. And that means that this approximation isn't sufficient to fully describe a first-order phase transition. And it turns out that we're going to have to go to higher order in the expansion in these thermal pieces to see that. But in any case, let me wrap it up here for today. Thermal corrections come in. They fix this quantum corrected effective potential, this quantum thermally corrected effective potential, such that you get so-called gauge for symmetry restoration at high energies. So